from Oslo from yesterday's session. That's a double thank you. It shows your commitment to learning and applying new technologies and new methodologies in your work. So thank you for that. And I would like to thank PA for allowing us to present such webinars. And it basically elevates uh, the uh, the level of performance that we do in oil and gas industry, especially with the digitization age that we're having, especially in the current decade. In today's session, there are going to be 0 theoretical slides on the topics. We're going to target 2 or 3 examples today. So it depends on how much time we have left. So we will try and we will aim for 3. But if we cannot do 3 examples, we are going to do, definitely we're going to do 2 examples. Please, if anyone has any questions, you can ask in the chat box, and I will try to answer that afterwards the session. So let me show you the first example. Oh, sorry, to be honest, this is going to be the second example overall, because yesterday we saw also an example. Okay. So in today's example, I'm going to show you how a well log can be used in machine learning. So we're going to try to build this well log suite, and we will use machine learning, and we will feed these data into machine learning, and machine learning will pinpoint some of the formations for us. It will highlight a few formations for you. We're going to use clustering for this action. Since clustering is unsupervised learning, it will show you some features in your data, but you have to understand what these mean. It's not going to tell you what these are, because the interpretation is very open. You have lots of capabilities to interpret this in any way you want, okay? Because this is unsupervised learning, there is no precise output for this. It can be multiple output at the same time, but the important thing is it reveals lots and lots and lots of hidden insights. Okay, so let's go ahead and start the first example, or to be honest, the second example overall. So what we're going to do is, in this example, we are going to try to generate this well log that I have shown you. And in order to do so, what do we need is, by the way, I already have the data at hand. Usually in the training, what we do is we already provide the data like a week before even the training start, and we teach them, we teach our trainees how to download the data, how to effectively get benefit from the data. Okay, so let me show you what the data looks like before we do start, because we are going to try to do we'll target multiple things at the same time. So let me show you. In yesterday's example, I have shown you how to work with Excel files. In today's example is going to be a little bit different. I'm going to show you how we can work with LAS files. So if for some people who don't know what a LAS file is, a LAS file is a specialized ASCII file that basically captures whatever you do in the well logging operations, or in the case of registering information from the well. So this is what the LAS file looks like. It's actually a specialized file, and it's quite common in oil and gas industry. Actually, it's very, very common in oil and gas industry. So the idea is we're going to read this file. And once we read the file, we're going to take the basic information from the file, like the start of the logging, the end of the logging, and steps. And basically, we're also going to get all of these parameters like bulk density, gamma ray, neutron density, the resistivity, and all of these parameters. And of course, we're going to get the data for all of these parameters. And we are going to insert these into machine learning. And we will tell machine learning, can you advise us of some insights or some pinpoints or some hotspots in our formations? And machine learning will just do that for us. Now, what does the machine learning reveals? It totally depends on what variables are going to be used for the prediction purposes. And I'm going to, by the way, I'm going to walk you through the process of selecting the variables. By the way, that's why one of the things that we also encourage people to is you have to have domain knowledge before you go into these types of tasks. Domain knowledge is the key to unlock these types of advanced workflows. Okay, so let me show you how we can read these files. By the way, if you take a look, it's almost 40,000 points in this well log file. So let me show you how we read these types of files. In Python, thankfully, we have a library for everything. And this is unprecedented in other programming languages. If you try other languages like Java, like C Sharp, like C++, by the way, I have a really strong background from C Sharp because I was doing C Sharp development for more than 9 years before I switched to Python. So there is nothing like Python, by the way, in the terms of the codes become so easy and because everything is basically facilitated for you. So you just type your code, just get your hands dirty with the code, and you will be amazed of what are the things that you can do, and basically in very short time. Okay. Number one, we need to read the last files, which is a specialized oil and gas data file. So let me show you how we can do this. In Python, the Canadian Well Logging Association has released a library called LASIO. So that LASIO will allow us to read last files. So we will do import LASIO as ls. So we are just naming it as ls. You can just omit this line. You don't need it. This is just something extra, by the way. Once we read the last file, I already have a facility file that basically plots the last file for me. This is something that we usually provide in the trainings. We type lots of code. We do lots of things. Some of the things that I feel it's standardized, we usually distribute in the training. So people, they have something they reference to all the time. So we have a library called Facilitate. So this Facilitate contains lots of things. One of the things that it contains is basically it will allow you to plot last files. Now we need to read the file. So the first line reads the file or basically allows you to read the file. The second one is allows you to plot the file. Okay. So let me show you. So we are going to create a file called, let's call this well log equals to facilitate read well log file. And basically this facilitation, it's based on LASIO. Basically, it allows you to read last files. So once you read the last file, you can just go ahead and print whatever last file you have read. And basically, it will be directly converted into a table for you. Now, do you see this? By the way, people who work in oil and gas industry, they know how frustrating it is to work with last files. I seen some people who are basically operating in mud logging units. They just copy and paste manually to Excel. But with Python, you don't have to do this. Python can interpret and basically decode the last file for you, and basically it returns a nice table for you to explore, by the way. So let me show you. You can also increase the number of units you want to see. So basically, you can interact with this, by the way. You can also generate a random sample of your last file. So let me show you a random sample of, let's say, 5 rows. So this is going to be randomly sampled from different depths. So this is just to explore the data. So if you hear the terminology EDA or exploratory data analysis, this function is one of these things. It shows you what different things exist in your file. Okay, so this is just to take a look. Let me show you one more thing that we usually do in these types of scenarios. We are going to see what parameters are available in our last file. So if we type well log dot columns, by the way, a column is very equal to the parameter or the mnemonic we have in the last files. So these are the parameters we have. Okay, so now it's time for us to start working with the last file, or it's time for us to start plotting the last file. Okay, because it's not very understandable what's happening in the last file. So let me show you how we plot it. It's just a single line because usually we provide these types of libraries. So facilitate get last plot. So we're getting our last plot. So open close parentheses. And of course, what we can do is we can just provide it with our plot, and we pass it the data. So we will say, please plot this well log data. Run this. There we go. This is your plot. Okay. By the way, this is a fully 100% interactive plot. It means that you can interact with it. You can zoom in it. You can do lots of things, by the way. So let me just zoom a little bit. we can select this zoom circle and just zoom on any portion we want from the well. Just do this. And of course, we can scan left and right. We can do basically lots of things. It's fully interactive. Let me show you one thing. This last file, by the way, I am walking you through an actual example that we usually we do. We work on this in real life scenarios. So one of these curves, which is the gamma ray curve, it shows a really high reading in the recordings. Usually, this is a problematic reading, or maybe there is some particular point in the last file that's wrong, or maybe there is something wrong with this formation. Usually, this is going to offset our prediction because we are using clustering, and clustering is basically based on the data density. So what usually we do is we are going to omit any value that we don't want. So let me show you how we can do this. We can filter this out very easily by doing a filtering action. So, sorry, let's do well log equals to well log where the gamma ray is less than 250 or any value that you're feeling comfortable with. Okay, so this is just out of approximation. If we run this now, you can see the plot is looking a lot better than before. Plus, now you don't have any values above 250 because now the values are truncated. Why? Because you filtered out the full table. So now this is what it looks like. Now, let me show you the idea. The idea is, and that's why I am telling you, you need some domain knowledge before you get into these types of things. Unfortunately, this is a common pitfall and it's a common mistake that is done by people who are, for example, students or they are in academia. For example, the people who are on the first years or master studies, especially on the first year, they try to embrace these types of things, but they don't understand the actual value of it because they don't have the enough experience to utilize these tools. Let me show you something. Usually in well logging, by the way, I'm not expert in well logging and well logging interpretation. I'm just showing you the possible use cases. Usually in well logging, we start with something called a reservoir flagging. It means that we differentiate which one or which layers are reservoir or potential reservoir, which one are not. Basically, the first criteria for this is your gamma ray. So any gamma ray reading that is low, these usually are responding to low clay content or low mud content. Usually, these types of low gamma ray are the targets of being reservoir. But how can we confirm there is oil in it or there's some type of hydrocarbon or some type of liquid in it? Usually, we correlate that with the resistivity, the density, the neutron phi. So we cross-validate everything together. But there is a problem. Usually, in order to validate this, you would need a petrophysics team, a team that is experienced in this quick look, let's say, interpretation or like an actual interpretation of this. So you need some expertise in that area. But let me show you something. Machine learning can actually help you in pinpointing which reservoirs or which layers are potential reservoirs, not just based on gamma ray. Because if you base your work on gamma ray, it's quite easy to know which one is which. Let me show you, but that's not going to be entirely accurate. I'm taking screenshot, by the way. Let me show you something. Usually what people do, they assume a certain percentage of the gamma ray to be like shaly or not. So what usually people will do, they will draw some line like this, and they call this a cutoff line. Anything on the right, it's not a reservoir. Anything on the left, it is a reservoir. Well, at least this is our speculation or the initial interpretation. But this is just based on a single track, or this is just based on a single plot. But this is very, let's say it's very subjective. Some engineers will push the line to the right. Some engineers push it to the left. If the oil prices goes up, the line is pushed to the right. If the oil prices go down, the line is pushed to the left. So this line is very subjective. It depends on lots of factors, and the most important factor is the engineering judgment. The thing that we need to keep in mind is the more the lines, or let's say the more the curves you add to the interpretation, the harder it will be, the more knowledge that you will need, and the more expertise you need to have. We will try to eliminate this in machine learning, and we will try to create an algorithm that pinpoints some of the locations for us in the well so we can start interpreting from these areas. Okay, so let me show you. Hopefully you have understood the idea. So first of all, this is the plot. Okay. What we're going to do is we're going to save the plot somewhere because we need to have the plot because we're going to modify it afterwards. So we will have a plot. There we go. Now everything's back to normal and everything is working. Now what we're going to do is we're going to train a machine learning algorithm that reads gamma ray, all resistivities, which is the deep resistivity and the intermediate resistivity. By the way, we do have two curves in here if you don't notice it already. So let me show you. So if we zoom in, you will find we have actually two or three curves underlying each other. Why is this? Because we have two resistivity targets, which is one is for deep and what one is for intermediate. Okay, so we will train also both of these. We will insert density to the training. And once we do these, machine learning should show us or pinpoint some of the locations for us. But there is one problem before we do start. Unfortunately, the density reading is not read all over the well. You can see the density reading is starting at depth of 3,000 something and ending at depth of close to 4,000. So what do we need to do is we need to filter down our data further in order just to include this portion, because above that, it's not very helpful. It's empty. Why you're predicting something empty? So we are just going to narrow down our data further. So how can we do this? It's easy. So we will do well log equals to well log where the index or the depth index is less or sorry, greater than 3,100. Once we do this, you can see now we're getting this plot, which is now the plot is narrowed down. Now there's two filters are interacting or opposed on the data itself. Now, why it's important to know Python in these cases? Because if you try to use softwares, usually softwares, I'm not saying they are bad. Actually, they are excellent in doing one particular task, which is like the regular interpretation. But if you're trying to do some type of analysis that requires some detailed, let's say, interpretation or some more advanced interpretation, most probably you will need Python. So if you think that you can get doing this in imp-teclog, for example, you can do so. But after a certain level, you will start incorporating Python also in teclog because Python is now in everything. And I'm not exaggerating, it's in everything. Once we have this, it's now time to create our model. So let's do model creation. So we will type create our model. Let me show you how we can do this. It's quite easy. Number one, we need the name of the model. So import clustering. So we have a dedicated library for clustering. Once we get the library for clustering, what we can do is we can create our model and we will say that we need k-mean clustering. By the way, we do have many algorithms for clustering. By far, the most used one in oil and gas industry is k-means. But this does not mean that you cannot choose other models. There are other models as well, but there is a justification for using these models, by the way. It's not just willy-nilly and selecting these models. There are some justifications, and this is basically what we teach in our training, why we are doing such a thing. Okay, now once we have our k-means, now between the k-means parentheses, now k-means actually requires something from you. It wants to know how many groups you want to divide your data to. Okay, so let's say that we want to divide our data into 2, 3, or 4 groups. Okay, so and it all depends. So let me show you something. If we divide our data into two groups, machine learning, what it does, it will read all your data. It will find any interaction between gamma ray, all the resistivities, and the density. And based on these interactions between the data, it will start to suggest hotspots, or let's say two different types of formations on your well log. So this is basically what's going to happen. You can do 3, you can do 4, you can do 5, you can do 20. The more the groups that you create, it requires you an understanding why you're selecting this much groups. Okay, but easiest one is to select the binary groups. It means that it's only two groups. It's either, for example, yes or no, reservoir non-reservoir, oil or gas, gas or oil, water, oil. So this is what it means usually. Two means that two separate formations are detected. Next thing is we need to select the X variables. So X equals to well log, open, close parentheses, and we're going to select the variables we want. So the first variable we are going to train is gamma ray. The second variable we are going to train is the bulk density. So how I'm knowing these? Because you already printed out the columns, and the columns contains all the names that you can select for training. Okay, so for other variables, we are going to use the neutron density, or the neutron porosity. We're also going to use the actual resistivity, and we're going to use the resistivity intermediate, and these are all the X variables. The next thing that we do is we are going to fit the model, or we will start training the model by, on top of these data. Okay, so let's do an X, run this. There we go. Now your model is trained. Once you train the model, but you don't, by the way, for now, you don't see what the data that are outputted from the model, because you need to get these manually. So let me show you. We will get all the data that was generated from the model, and the model generates two things for you. It will generate each formation or each point in the formation and to which group it belongs to, because now you have only two groups, group 0 and group 1. These can be anything you want, and it depends on how you interpret the model. So that's why some information about the domain is very important. We will say model.labels, and we can use the labels to color these points. And this is what we are going to do exactly. So let's run this. There we go. Now this is our log plot. We will just leave this for just 1 minute, and I'm going to show you a different plot. So if we do a plotly plot, we are going to do a scatter plot for a cross plot between the gamma ray or any parameter we want. So if we do a scatter plot of our well log, and on the x-axis, we decide we want to see gamma ray. On the y-axis, for example, we want to see the bulk density, right? So if we run this, so actually we're missing something. So the y is bulk density. There we go. Now this is what the data looks like. This is your raw data. The data, to be honest, it's meaningless. Why the data is meaningless? Because there are no other context to this data. Context means that shapes, colors, groupings. So we don't see anything in particular. So everything is in there. What we can do is, based on these X and Ys, which is the bulk density and the gamma ray, we already have grouped our formations in the model. We are also getting these in the labels. So what we can do is we can get the outputs from the machine learning and just color these points based on the machine learning output. So once we do this, this is what the output is going to look like. You have two different types of formations. One formation is denoted with this blue lines, and one formation is the one that's denoted between in this yellow lines, yellow dots. So if we zoom in, you can see these. These are basically the different points in the formation. Of course, the more data you add to the training, the best the training it becomes. One of the reasons that you might not see correct results from this model is because you're not using the proper versions of the data. Usually what we do is, since the resistivity have different scales, and the scales of the resistivity is way, way higher than the gamma ray or the density, so this is called a incompatibility in scales. Usually we use a simple scaling technique. So let me show you a very simple scaling technique. So we're going to use a pre-processing, and we're going to create a scalar. So basically it will normalize the data between 0 and 1. That's it. That's all you need to know for now. There are many, many scalars that we can choose from. And usually this is part of the training that we do. And once we do the scaling, we can do something like this. X scaled equals to scalar dot fit transform X. Basically, we are giving it our data and we tell it, please take the data and make it between 0 and 1. So everything is compatible and everything has same importance in the machine learning. Once we do this, now we can run this code again and you will get a slightly different results. So scaled, run this again. There we go. Now basically it groups your data into two. This group that's basically in here and this group. Let's see why it's doing this. Because the bulk density is 0, by the way, so that's why it's being grouped together. So this is one thing that we also need to adjust. The bulk density is never 0, so there is a problem with this. What we're going to do is we're going to add a third filter for this. So basically it starts working properly. So we will say that well log dot bulk density is greater than, for example, 1, because usually it's not less than 1, by the way. If we run this again, there we go. Now the machine learning model starts to work properly. Now, what it did, it separated your model into two different groups. And of course, there are some overlapping in the groups. But what do these groups represent? It's really hard to tell unless we start to plot it on this empty track we have. Okay, but it's most probably it's showing you the formations and which ones are not the formations. So let me show you how we can reflect the plot as well. Let's import a library that allows us to modify this. So import, let's do plotly dot graph objects as geo. So we're basically going to create a line chart. A line chart that's going to be added to the existing plot. Okay, so what we're going to do is we're going to do plot dot add trace. We're going to add a new line to this plot, which is going to be sitting in the last part of the data. So we will say that this is a line plot. The X is basically your depth. The Y is, actually it's not last, it is well log. The Y is basically anything you want. By the way, anything you want to plot. For example, I can do gamma ray. You can do anything you want. So we're going to do gamma ray. And of course, we need to tell it where we are going to set this. We're going to set it at the last column, which is column number 4. Okay. Actually, this is wrong. The Y should be on depth and X should be on the gamma ray. So that's my bad. So this is the new track, but the new track is nothing special. It's just a line. We need to reflect the machine learning points in this because we have two different formations that were detected by machine learning. So we need to reflect that on this plot. Let's do that. We will say that we only want to see markers, or let's say we want to see the points. We don't want to see the line. This should be scatter. Let's see that. Actually, this is mode, not models. Yeah, there we go. Now we have now scatters. What we're going to do now, we're going to follow and color these points based on what the machine learning is providing us. And One final thing that we're going to provide is actually the marker color, which is going to be something like this. So let me zoom this in. So marker underscore color equals to label, run this. There we go. Now this is your marker coloring. And both of these plots, they basically, let's say they match 100% on the colors, by the way. So the yellows on here, I basically presented on these, and the blue ones are presented as well. Now let's start to explain this model, why we got this type of data. First, you can approach the explainability of this model by doing two things. Either you go with the potential formations, or you start with the formations that are not potential. For example, any formations that show high gamma ray, it's a clay formation, especially if you're working with conventional oil and gas fields. So these are a no-no. So we don't want these. Or actually, we don't, usually we don't drill for these formations and we don't perforate them. So if we zoom in these types of formations, you will start revealing some patterns. So this formation is starting from 3 to 100 and ending at, so it's a 30-meter formation. And you can see this formation is potentially, it's not a reservoir and it does not contain anything. And it's blue. Now, we started to understand the model. The blue means that there is no oil and there is no potential for the oil in this. And this is how we're going to explain this further. So the blue, it means that there is no oil. So whatever you see blue, it means that there is no oil. Wherever you see yellow, it means that there is something in there. And this is how usually you proceed forward by explaining this model. So if we zoom in on this model or on this portion of the data, which is all yellow, there is a great potential in this. And now what you're going to do is you're going to cross-validate this with the gamma ray, with the resistivity, and of course with the density and other parameters. This is all with the help of the machine learning. So what we are saying is, as a conclusion on this, what we are saying is machine learning can potentially help you in interpreting the data, but it's not going to interpret the data for you. So you still have to have some domain knowledge. Okay. So this is the first example. Please make sure that you have your questions ready. So because once we open up the chat box later, so you can write down your questions. Please try to ask technical questions if possible. So this is the first example. It's a simple model. It basically shows you how the data works. One final thing that you can do is, instead of just doing two groups of data, so let's see, we can do three groups of data, or we can do five groups of data. But keep in mind, the more groups you incorporate, the harder it is for you to explain the model, the more knowledge you need to have domain-wise, not machine learning-wise, but domain-wise. Let me show you. So if I run five groups, you can see now your machine learning model is divided into five groups. And do you know what's the great thing about this? Yellow is still the ones that are potential reservoirs. The other ones you have to interpret it. Maybe these are different rock types. Maybe these represent some particular feature in your data. You need to know what these other colors represent, but most definitely the yellow ones are the potential reservoirs that you need to look for. This is all based on multiple training features at the same time. It's based on these five curves. It's not just based on the one curve. No, it's based on five curves. We're getting this result. This was the first example, which is clustering the actual petrophysical data of a certain and given well. Now let's move to the next example. Next example, I am going to just to show you how we can do a map in machine learning. Okay, so this is not going to be a full example. This is just going to me going to show you something. Okay, so let's try to do this. Okay, so let me just copy the data. Let me paste it. So in this example, we have a table called data frame. This table contains multiple columns, and these are the X and Y headers for the wells. So it contains the name of the well, it contains the thickness of the pay zone, the porosity, the water saturation, The recovery factor, so this is missing data. The gas recovery factor, we have also the total depth or the target depth of the well. Yeah, basically what we usually do, we create a base map around this. Okay, let me show you. So if we do, for example, just pay attention to this. If we do contour plot, we will use X and Y and Z. So the X is the X location for the wells. Y is the Y location. Z is the depth of these wells. You can do other parameters. You can do, for example, porosity. You can do some vertical seismic profiling. You can do anything you want. Once you run this, let's see. Yeah, actually, it's try contour fill. You will get a contour that is actually, it's somewhat ugly. A contour that looks like this. Of course, you can enhance this and change the map or the color map, by the way, for rainbow or any color other map you want. Yeah, but it still remains ugly. Why it's ugly? Let me show you. There is a reason for this. Yeah, there is a reason for the ugliness. Yeah, that's the statement. So in oil and gas applications and oil and gas fields, we have two things that we need to keep in mind. The oil and gas fields usually are big. They are big in size. Let's say that we have a field of 20 kilometers by 40 kilometers, which is quite normal for oil and gas fields. But if your field is good pressured, it has some good saturation, it has some thickness to it, it has some great permeability, most probably you're not going to drill lots of wells because the existing wells might cover and basically contribute to a good production. For example, you decide, for example, to drill 200 wells in this area, right? Maybe you don't go for 400 and 500. You just go for 200 wells, maybe even less than that. What this happens is in oil and gas industry, whenever you decide to drill for wells, your decision is based on data. It's not based on geography, right? We don't care about geography. We don't care about perfect triangles. We don't care about rectangles. We don't care about sections. We follow the porosity, we follow the permeability, we follow the saturation. It does not make any sense for us to follow rectangular drilling if there is no oil there. It has to have oil. So this is basically one of the basics of selecting the initial locations for the wells, at least. This contributes to a new problem and significant problem for us. The spacing between the wells are not equal. There are different spacing between the wells. And the more the space the wells are, the more space is left between the wells unexplored. So let's say this well has 2 kilometers spacing. These two wells has 3 kilometers spacing. So the more the space you have between the wells, there is the more uncertainty you have in this area, right? Luckily, we already have existing algorithms that solve this problem for us, but machine learning is just another algorithm that helps us in that area. So let me show you. We can convert this very, very ugly map into a more beautiful map that is constructed by machine learning. So let me show you. So we can do import facilitate as FT. So in the facilitate, we have the function that basically can plot for us or convert this chart into a machine learning predicted chart based on the algorithms. So create map. Once we do this, let's run it. It says that X is not defined. So let's see. Let's get the full code. Let's get the full code for this. Copy it, and we can of course paste it in here. There we go. Now this is what the machine learning will generate for you. It will convert your boring map into this beautiful map. And it's not just about the beauty. It is about the proper interpolation and proper placement of your data and proper placement of your distribution of the properties between the wells. So these X's are the wells, and the colors are basically the water saturation that is, or the depth that is interpolated based on the machine learning algorithm. Of course, there are other ways, but this is a very modern way of doing so. And Petrel software also does this at certain level. So this is just another example. Now I think we have 15 minutes left. Let's go for another example, if times allow us to. So let's create a new example. So let's get pandas to read some data. So data, let's read the data. It's a CSV data. So it's called well data.csv. Define. There we go. So let me show you what this well data is about. So this well data, each point represents a particular operating condition in certain wells. Okay, so the first column is the depth, the second column is the wellhead, the third column is the density, gravity, water gravity, and so on and so forth. So plus we have some well testing data, casing ID, tubing ID, and we have basically some data in there. Okay, but the most important thing is we have a column called the status, or basically the status of the problem. So each well is labeled with a particular status. The LU, it means that it's loaded up. Unloaded, it means that the well is clean. There is no fluid accumulated. And this is basically what all of these labels mean. And what you see in front of you, some people call it categories. Some people call it events. And in machine learning, these are called labels. So no matter the names you call it, all of these refer to the same thing. It's basically describing the event, or basically describing the status of your condition. Guess what? In machine learning, we can select any of these numerical columns to predict these events or these labels. So what this allows us to do, this allows us to do two things. We will create a model that predicts in the future for us the status of our well once it comes from the field based on the new arrival data. Number two, we can construct a two-dimensional color map that show us exactly these problems. So let me show you how we can approach this. Number one, we're going to import a machine learning model that does these problems for us. And this problem is called a classification problem. There are many ranges of libraries that you can use for classification. And I am using XGBoost for this. By the way, in the training that we usually explain why these models are working, which one you should use, which one is the most common one, which one is the least common one, which one is just muscle flexing, which one will not work well. So all of these things usually are explained in our training because it's 2-month training. It's built to teach you these things. So let's create a model. Let's call this XGBoost dot XGB classifier, because this is a classification. We will feed numbers and get labels, or we will get categories. Before we do that, we need two things. We need features and we need the target. So what are the columns that we are going to use for prediction, and which columns that we want to predict, or which columns that we want to understand how they are behaving? So we're going to use columns. So for the features, or let's say for the X variable, I am going to use the well test data. So these are how much cubic feet of gas we are removing from the well during the testing. And I'm also going to select the wellhead pressure. By the way, if you have PWF, if you have, for example, total liquid removal from the well, if you have like any chemical injection, you can also, dosages, by the way, you can also include that in the training. The more the data that's related, the accurate the model will be. What I am trying to predict is status during test. These are the state, or these are the labels. Okay, so that's why this is one of the things that I've told you in the first session. Machine learning is the only model that can predict these labels based on numerical data. We don't have such an equation in oil and gas industry. And this is all the physics is learned by the machine learning by running different simulations or by running different iterations in the model itself. Now it's time to train the model. So we will say that model dot fit. Fit, it means that we are training the model. So data frame, so we will train it based on features and we will basically getting the targets. Okay, so we will run the model. Let's see what the problem is. Yeah, it says that it cannot accept labels, but yeah, that's okay because we can switch to other models that can accept that. By the way, some models in machine learning, they do not accept text as a training parameter, but others do. So yeah, that's why we use Python, because we have lots of options. So let's switch to random forest classifier, which is a classifier that's also used in Petrel and Schlumberger softwares. So let's run this. There we go. Now the model is working. Of course, we can get the score for the model. So the result for the score is just, I will take the model and then I will score on it. And I will print the score so I can show you the accuracy or correctness of the model. So score equals to the result that we got from the model. There we go. The score is 1. It means that this is 100% accurate. Actually, usually it's not 100% accurate because we have low amounts of data. So that's why if you get like more data, chances are the model is going to be less accurate, but it's more generalized. Anyways, this is something that we usually teach in the full training. Once we have this model, what we can do is we can create a boundary for our model. So basically we can tell where the problem is happening in the operation envelope. So let me show you. So if we do sklearn.inspection, so basically we are inspecting the model. We will say that inspection dot decision boundary dot from the model or from the estimator. We will say that take the model, take our inputs, which is the features, and please generate a boundary for us. So let me show you. If we run this, there we go. This is the operational boundary. You have 3 colors. 1, 2, 3. Each color is representing a particular domain of operation. For example, loaded up, unloaded, and the near loaded up. You can, of course, get the figure as well, and you can control many aspects of the figure. For example, you can control the resolution of the figure. You can control the color map of the figure. So we can make this rainbow, or you can do any color map you want, by the way. And once you do this, you can also control, for example, if you have like low flow in the well, it's going to be squished in this place, okay? So let me show you one thing. You can do figure.axis.scatter. We can also plot the wells, by the way, if you didn't know that already. So we can do a flow test on the x-axis. We can plot the locations for these wells. This is going to be the operational locations, not the geographical locations. We can just copy and paste these. So this will basically show us which well is performing at which boundary. This is what it means. Let's run this. There we go. Now these are the wells. We can, of course, give them colors. I will make them black. So they pop up. There we go. You can see there are some concentration of wells on the really low margins. Why this is happening? Because these are low data. And how we can fix this? You can fix this with your domain knowledge in oil and gas industry. Now, what happens if you want to maximize the small scale and minimize the larger scale? You already know this from well testing. We use log plots for this. So let's do figure axis dot set y scale. Let's set the y scale to log. Run this. Now it's looking a lot better. And we can, of course, do this for the x-axis. Now you have a full operational boundary for which flow is basically contributing to the problems and which are not. Most definitely, the red region is the safe region. This this Azure or Azure similar region is basically the region that has problems, and anything in between is unquestionable or it's nearly loaded up or there is some sort of a problem in it. This is known as a decision boundary, which is very, very similar to the flow regime maps, but this is based on machine learning. So one final thing I'm going to show you is if you use your machine learning model that's already trained and feed data into it, and once you feed new data, the machine learning model should tell you where the data, what's the type of the well you have. For example, we we used um, we used testing rate and we used wellhead pressure. So if we provided these two variables, the machine learning should tell me what the variable or what's the parameter we have. Okay, so let's say that in the testing we have 1200 gas rate and the wellhead pressure is, let's say, it's 500. Okay, so if we run this, the machine learning model will tell you that this is a well that is loaded up. You can use multiple predictions at the same time. So if you have like future data or wells that you don't know the status for, you can use this methodology. So let's say that the wellhead pressure is 800 and the flow is, it's quite opposite. Now you get two predictions. Yeah, this is how you can use the machine learning model to do classification. And I've shown you how to show them do the machine learning to do digital mapping for the X and Y maps. Plus, I've also showed you how to apply that on clustering for well logging analysis. Yeah, these are three examples that I promised you with. And yeah, that's all from my side. Thank you so much. Now, Nikhil,